All right, that lined up pretty dang well. I claim. I don't know. We'll have to see on the replay. But yes, welcome to episode 5 of My Monastery Life. What's the deal with neutrinos? Hmm. Now, I use 3Ms for a reason, because apparently there's 3 different flavors of neutrinos. Are they the tastiest, difficult to detect substance in the multiverse? I don't know. But we're going to lay out a little bit of the stuff as different folks can start to roll in, just unwind and stuff. And if anyone's actually curious, like, always rewatch if that was something they were feeling the urge to do for whatever reason. I ain't here to tell anybody what to do. I'm just a dude rambling on the internet. And as a dude rambling on the internet, I should probably throw in my other earbud because then it helps me focus and it sounds more balanced as it's into both of my ears and we're in stereo. And I should probably actually make sure we're on the correct audio devices. That would be useful. Yes, yes, professional YouTubers here. All right. Input bomb. All right. So I think we're doing okay. All right. You can close that out. All right. So today on the plate is, as we can see on the board that I actually used and had to edit out because I had JTV over here initially. But all right. What's the deal with neutrinos? On front, I don't know. I don't know. Again, not a professionally trained physicist nor mathematician. I'm just a dude on the internet that has been extremely blessed within my life. And as a gamer, which I don't know if it's a good thing or a bad thing, that's probably my longest held identity. Gamer, the point of a gamer is to play the game. Play the game, you see different sequences, you see different patterns, and you try to figure out things. I'm not saying the confidence I have in there actually being really something to this, something truly substantive, is probably about the same as the number there. Really, really small, but at least it's an idea, and we get ideas out there so we can synthesize, we can critique, we can give a little bit of analysis and be like, oh, well, if you did this and this, that would make a lot more sense. Okay. So, as far as we know, apparently, to my knowledge, neutrinos are not part of the standard model because we don't really know. Apparently, and this is something that I had first heard. Yeah, I had kind of gone through the papers, but I'm like, all right, I don't really see a lot of significant digits, but I can see some magnitudes and stuff. But apparently, from Professor Keating, shout out to Professor Keating in the Into the Impossible podcast. Um, we've managed to narrow the range of the massive neutrinos, or at least the sum of all 3 flavors. The neutrinos are supposed to come into 3 flavors. Typically, the electron neutrino, the muon neutrino, and the tau neutrino. Now, we'll get into some math and a little bit of stuff and things in a little bit. I got some tabs. I'll hopefully remember to add them into the thing later. But ultimately, we found, let's just do one of the first ones right now, because that will make things much easier. All right. Because I'll just follow my standard route of seeing what we can figure out here. All right. Hey, Hex. Oh, Hex is claiming that the muon flavor tastes best. Uh, it's oh, am I in a cult? Probably. Uh, that's the thing. That's why I also stress that I'm not telling anybody what to do. You do you, boo. It's my general view of it. It's yes. Yeah, Jack, yeah, that's probably not bad advice. Jack's commenting. Life is a long life is long, crazy, long, so stop acting like you're in a rush. Yeah, yeah, yeah. Hey, maybe we're all going off the rails on a crazy train. But where was it? Uh June 17th. Let's go to this guy. This was from sciencenews.org, so take it as you would. Basically, my path through this was right over here. So they're going over apparently neutrinos oscillate. Apparently, somebody won a Nobel Prize in physics for it, and I think in 2015. Let's see. But basically, what they've apparently managed to do is to collect enough data to get to about the correct magnitude. I say about the correct magnitude because you got to include the error there, and different experiments might give you different things, and we're honing in. But apparently, there was a problem. What was the problem? Okay, so as we can see, an electron volt is a unit physicists used to quantify mass. An electron's mass is about 511 electron volts, or was it 500, like 0.511 MeV, mega electron volts. That would be a million right there. I remember that from Final Fantasy because the different versions of Bahamut, it would have it would have mega flare, giga flare, and then tera flare. Because mega is a million, giga is a billion, tera is a trillion. That's just how I remember it in my head. And then you had Exa and everything. So and then it continued on in the other Final Fantasy. Okay. What are they saying here? Blah, blah, blah. Okay. So as we see, neutrino detectors can spot the shapeshifting because of oscillations, blah, blah, blah. But they do indicate the sum of the three neutrino masses must be greater than about 0.06 electron volts. Okay. That's ridiculously small because, as I said, an electron is about 511,000. And according to the standard model, that's the smallest in mass particle that we have because protons are like 4 magnitudes greater. What is it? Yeah, it's like 1,836 times as massive as an electron, something like that. All right. So the problem that they have is they found a top. That was the bottom threshold. So where was it? Oh, I swear they had it right there. Or maybe I'm just reading a different article. I know. It's here we go. Okay. The DESI data in combination with the cosmic microwave background data from the European Space Agency's Planck satellite provides a mass ceiling for neutrinos. So the sum of the three masses is less than about 0.07 electron volts at a 95% confidence level. I was right in front of my face as I was reading something else. I'm sorry, I get distracted by numbers. Okay. So what they're saying is we can get back out of this. Okay. So what they're saying is, according to DESI and the Planck satellite from ESA, they've established what they believe to be an upper bounds on the mass of all three neutrinos combined. So if we add all the masses together, they believe it should be less than about 0.07 electron volts. And apparently from lab experiments, and I do have some of the other articles where they do start to go through it, but I wrote this down because I was still searching for it. According to other experiments, the lower bound on the mass of all three neutrinos is 0.06 electron volts. Okay, for those keeping a track, we're at the same magnitude, a 0.0 between 6 and 7 electron volts. That's a very narrow range if this is accurate, and there is reason to believe by a number of folks that this is probably pretty accurate because we have amazing technology. Any sufficiently advanced technology is indistinguishable from magic. Again, I learned that from Professor Keating, and that was provided to us by Arthur C. Clarke. Is that the case? I don't know. It's a fun thing to think about, though. Okay, so according to the whole thing, we have a very narrow range for the mass of all three neutrinos. Okay, and as you can see, there's already something written here, so it's anybody wants to play on Wolfram Alpha or whatever, you can do this and verify it for yourself. Um, but I got to thinking, at least within the model that is constructed, and we got there on the poster, our elementary unit, the electron, which basically we're using to help scale everything else with, it's based upon a construction like this. So basically, we'll just do, We'll do the full electron because we're claiming it. So the mass, the electron, we're using a minus sign because, well, that's easier. Actually, no, let's just do m sub e because just for lack of confusion. Okay. The mass of the electron, we have it equal to. All right. Now, this is a very fun trick that you can do very easily. All right. You take the Planck mass, m sub p, you raise it to the fourth power. Now, remember, that's also going to give you 4 dimensions of mass. But that's not the expression we're looking for. It's a single dimension of mass we need to solve for. All right, so we divide it by kilograms to the third. That seems very arbitrary. I agree. Unless we factor in something that's like, all right, maybe there's some more orthogonal nature to reality. Maybe if we kind of almost in my head, I'm viewing it as like a Cartesian plane here. It's like, all right, we got our X, we've got our Y here, and then we got some quadrants. Okay, we got some quadrants. Maybe they're all lining up, and maybe it's curving in a particular way that may be hard to detect for observers like us. I don't know. And it appears to be spatially 3 dimensions. I don't know. Do we get a single dimension out of our 4-dimensional hyperbolic space-time divided by the expression of the base unit to the third? It gives the right dimensions. Oh, that gets you, I believe, the first couple of digits for the mass of the. No, no, no. It gets you to right about the magnitude. You also just need. It's a little smaller because we're going to add a prefix here. 4 G. I can express it the other way because I am a savage, and we should still be commutative in this nature. All right, get that. Boom, boom. 4 G G I. All right. For those that have been paying attention and maybe following some of this work for a little while, that is the volume of the Giesking manifold. It's the simplest it's the minimal non-compact 3 manifold. So minimal non-compact 3 manifold. Okay, there we go. Try saying that 3 times fast. Minimal non-compact 3 manifold. Minimal compact non-3 manifold. No, minimal compact 3 manifold. Minimal non-compact 3 manifold. Okay, that is hard. I digress. But you get that, and let's do that out right now. Why? Because we have the internet. And apparently the chat managed to convince Stephen Wolfram to live in his natural computational habitat, and rather than trying to think through all the things, it's like, well, you kind of are the dude that created this symbolic language to help make answering these questions easier, so you don't need to remember everything. So maybe he will actually start to do that. But we shall see. I cannot confirm, Hex, if the missing neutrinos are found. It's a fascinating thing because I'm not really exactly sure what to make of the expression. If there was something to that, it's fantastical. Oh, hey, Mark. Good to see you. But yes, a lot of these things are very, very. It seems crazy. I mean, maybe crazy beautiful. I mean, E8 is a fantastic thing. And actually, if you look at the graph map of the, I believe the 600 cell, it looks eerily close. Oh, you know what? Let's do this. Find E8. So we'll bring it up. And screen. Actually, I think we can just do it on Wolfram. And this guy. All right. Wolfram. Try this. E8. I don't think it's. No, that's just doing E times 8. Okay, I'll go back. Yeah. All right, E8. Just go to real quick image. Oh, wow. Look at that. Isn't it beautiful? Look at that beautiful graph layout. Do I know what all this means? No. Because it's supposed to be an 8-dimensional thing and they're trying to express it in 2 dimensions. Okay. But then we go over to Go back to Wolfram. So I know this is in there, the 600. So yes, this is where a dash actually makes a difference. So we'll go to its representation of the graph. Oh, looky. And maybe some more images. I think it's the same thing. Okay. Now again, maybe this is just because this is a hypergraph, because E8 I believe would be a hypergraph too, because it's higher than a standard two-dimensional graph or even three. So we call it hyper once we get up to things that are, I don't know, more powerful. Is that how Sonic the Hedgehog works? It's like you have Sonic, you have Supersonic, you have Hypersonic, kind of like a Saiyan, you get a Super Saiyan, a Super Saiyan 2, etc., etc. I don't know. That's just how my mind works. But all right, so we got the 600 cell here, but that's not what we're actually supposed to be doing here. We're supposed to be taking the Planck mass and we raise it to the fourth. Because remember, if we're raising it, and based upon our unit system, it ends up just keep getting smaller and smaller and smaller. All right, so that gets us to about 10 to 2.2 times negative 31. All right, so just divide by kilograms, divide by 3. Excuse me, raise to the third power. All right, so what is that? All right, oh, we're at about quarter of the electron mass. Might we need an additional component? Additional we shall add. For Keysking constants, go there. 4 GGI times the Planck mass raised to the fourth divided by kilograms to the third. What a crazy expression there. What's I guess? 9.109 times 10 to the negative 31 kilograms. Oh, 9.109, etc., times 10 to the negative 31 kilograms. Don't that just beat all? Oh, there we go. We got our 0.511 mega electron volts. And then we divide that by c squared, and then we get our mass output equivalent, or the mass equivalent of that energy. Cool. So we have that. Oh, yeah, and then we need, let me just double check. I think it's 1 plus, that's a pretty thing. I haven't had it all committed to memory. Because you can also express in a couple of ways. 3, blah, 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 blah. So the electron, that's deuteron. There we go. Root 18 over root 2 BFE. Okay. So that would be, we need to have our second part of this. The second part is 1 plus, because that's how we start off, because we're attempting to be coherent here. Oh, I should actually take this down. God. Can barely see to begin with. All right. And then this is our expression in here. All right. It's the square root of 18 over the square root. Now I'm writing it in this form. We usually use 2 VFE, but you can do the same thing. Or G D I. And that expression, we get our J component. It's J R, so a radial component raised to the third power times our little inversion box here. And then you will get the electron mass to, with CoData's new listing, I believe it's about 0.23, maybe 2.6 sigma. So it's well within 1 sigma of the current thing. And God, that really helped that tightening those measurements. And that's what we're hoping for the neutrinos here. Because it's like, okay, this might have, and then we have the electron mass, probably like 12 significant digits, something like that. A lot. What do we have the neutrino mass to? 0 significant digits? Maybe 1. So in order to actually have an accurate picture, we're going to need better measurements. Okay. So we have this here. And again, just to go over this for those that may be kind of just joining us or watching this temporarily in the future for the first time, what are we doing here? Well, let's move this down a little bit so we can see a little better. Okay, so the claim is this equals the mass of the electron. So what are we doing? We've got some dimensional stuff. All right, we've got the Planck mass raised to a 4th power. So I'm thinking, okay, maybe something orthogonal going on here. We got a thing, a thing, a thing, a thing. Okay. And we're dividing it out so we can get them the correct dimension by kilograms to the number of our observed spatial dimensions. All right, that's interesting. That reduces it to a single dimensional component. Then we're multiplying it by, wait a second, we got 4 Planck masses. We've got 4 Giesian constants, which coincidentally, if you think the Giesian constant has nothing to do with it, that's totally fine. It's also the volume of a hyperbolic tetrahedron. I'm just saying, because it's made of a hyperbolic, of an idealized tetrahedron. So that should make sense. And this will get it correct to about, I think about like 7 or 8 significant digits. So we got the mass measurement to 12. The thing is, the claim is at approximately the magnitude of vacuum permittivity. So basic view of E naught, it's about 10 to the negative, it's like 4 pi times 10 to the negative 7. So the claim is right around that point, something very interesting happens because most of our Planck constants, with the exception of charge, and again, charge is a separate issue. I'm just making that clear. We have a difference between what is colloquially used. There might be some reasons for that. We could be wrong. Otherwise, things might get even more interesting. But an interesting thing happens. Is there some dimensional mixing going on once we get to a very specific magnitude and range? I also think, what is it? Is it around 10 to the negative 7 meters? Maybe it's 10 to the negative 8 meters. Something around that magnitude. I believe I had heard from Professor Green was that apparently the standard Stern-Gerlach experiment. It's like, oh, look at the double. Basically, it stops working once you get to around that magnitude. And I have no idea. I'm not an experimentalist or an actual particle physicist. I just spend excessive amounts of time using Wolfram Alpha and just going through and reading and listening to other crazy people like myself on the internet. Why? Because you never know where a good idea may come from. Okay. Oh, you let the hair down. Oh, it's getting a little hot. All right. But the claim is something interesting is happening. So this magnitude is set as the Planck mass times the Planck length, L sub p, over the Planck charge, which is Q sub p squared. And that is approximately 10 to the negative 7. More appropriately, it's like 9.99999, I think, 1,999 times 10 to the negative 8. Pretty close to 10 to the negative 7. But what did this do? Since we have 1, and now we're using this as an offset to get our second piece. So, and when you solve for x and everything, this was the best fit. And then you also look at it, you're like, all right, well, that's got 4 Giesian constants. And the inner part is the square root of 4 Giesian constants. And then that's within the square root of 18. What the heck is 18? Well, 18 is our claimed number of derangements for the charge boundary, because the Planck charge is of the magnitude 10 to the negative 18. And if logs are useful, maybe we can gain some intuition. Again, I am very, very biased on this. I've spent a lot of time, resources, this, that, the other thing in this. But I also was taught to follow the evidence, because my dad, God rest his soul, he was an attorney. He's like, number one, the truth is the ultimate defense. It may take some time, but the truth is to fully get out there and be accepted, and that's if it ever actually does. That's a factor, but you also follow the evidence. The first thing that got me here is, oh, look, no, there seems to be new physics. Nobody knows the muon G2 thing. And now with a lot more brute force QCD, I believe or lattice QCD, I think they've been kind of able to figure it out, or at least they propose. It's like, okay, we just had to throw a lot more compute and analysis at it. Is that right? I don't know. A lot of people seem to think that, but it was the sheer fact that Thad had premiered his thing where he correctly predicted the muon G2 results the day before. That got me interested. So you look into the methodology, and okay, maybe that's not right, but there's about 288, to be fair, probably more like 300 or so predictions that we have now. Some of them are probably going to be wrong. Occasionally, there could be error within experiments, but I'm happy to be wrong because the more digits we get, the more we're able to refine things, the more beautiful things are able to get. Because I ain't gonna lie, it's the answer we had before that. It's like, okay, it was kind of cool. This is very pretty. Confidence in this goes from uh, greater than this number. I'll leave it. I'll leave it at that. Whatever your Bayesian priors are, hey, power to you. Uh, but okay, we can put this all down because we don't need this at the moment, unless, yeah, no, we'll wipe it down because I'll confuse myself and then go sidetracked off. Don't worry. Don't worry, chat. We'll be right there. Let's catch up. I saw there was some activity. All right. This is where it's good to have a co-host, even if your co-host seems to break everything. Although I do resemble that remark myself there. Okay, what we have here. Hex commented that E8 is apparently either a reduced form of a higher dimension. Yeah, because I think they had, was it a double cover? Something, I think the reason why a lot of folks like the 26 dimension thing is because I think that's like a double cover of the Leech lattice and has a lot of nice properties and everything would be solved or people conjectured, but this thing is so ginormous. It's like, I don't know. I think, because I know Nick from the Wolfram Institute, he's been using the 600 cell, which is basically a hyper icosahedron. It's the it's basically if you take a 20-sided die from Dungeons and Dragons, that's an icosahedron because it's got it uses all triangles, it has 20 sides, and then at each vertex you're going to have like basically 5 triangles kind of like fitting in there and everything, and then it closes 3-dimensionally. Now the 4-dimensional version is the 600, so that crazy kind of graph we were looking at a little bit before. But no, it's very interesting. Uh, yes, listen, I'm not saying this is a traditional monastery. Maybe we should brew beer. Maybe we should do all these other things. I cannot confirm nor deny any of that. But let's see. Oh, just let's see. Yeah, well, my brain does change all the time. Okay, so what was I looking at doing? Okay, we're just checking in. All right. Well, it's good to have you here, Jack. So let's get back to what we're actually doing over here. All right. So what the heck is this expression? This expression leads to this number. Now, again, I just kind of looked at these. I'm like, all right, we're at a magnitude. So the whole reason I showed that other thing about like the mass of the electron is with the Planck mass to the 4th power to give us within the standard model of particle physics as I know it, or at least I'm aware, basically the electron. Basically, okay, maybe there's some other leptons, there's something going on, maybe there's another within the Zoom particle that's smaller, but as far as like an elementary particle or whatnot, it doesn't seem to get smaller than like an electron. Okay, that was the Planck mass to the 4th. So I'm like, all right, what if we did basically the exact same thing but we went to the 5th power? How can we justify that? Well, we're claiming there's 5-dimensional ingredients that we have within our reality: time, space, expressed as length, charge, mass, and temperature. Those 5 ingredients, we can get the constants of nature. Groovy. So what if we just assumed that was a maximal expression in order to get the minimum value of mass? I mean, that's totally crazy. I mean, it's off. It's off until we multiply it by 8 pi. I don't know. See, I tried to find structure constant or Joe one and the different roots and different powers, and it was kind of going around. And then when I summed all the neutrinos, I'm like, but it's just a base calculation. Well, if we need to be between 0.06 electron volts and 0.07 electron volts. This happens to get us 0.06885 electron volts. I'm sure there's some error in the last digit or so. But I'm like, all right, so 0.068 is between 0.06 and 0.07. Now, again, these magnitudes could be off. And again, my level of confidence in this is okay, maybe it's a little bit greater as like a first. It's probably about this for the actual level of confidence because we don't even have one significant digit. We think we've narrowed down the magnitude. That's fantastic. Does does that mean that's the answer? Almost certainly not. But it's just a fun thing to do, and maybe there is something to this. Why is it that the Planck mass to the fifth divide by kilograms to the fourth? It gets us into the ballpark. Now you're going to need to have a pretty good connection to actually knock it out of the park, and we're we're going to need more than zero significant digits. So just just because I mean that's science. It's like I could say this. I could go out there and say something just even crazier than I normally do and be like, can't you see this is obviously the answer, bro? Blah, blah, blah. Utilize charisma, say a whole bunch of fantastic words, go attack a whole bunch of other people, tell everybody, oh, it's the establishment, oh, it's tearing everything down, blah, blah, blah. Confirm people's biases. Why? Because that's the current business model. All right, that rant is over. But no, literally, I mean, like, I went to school for business. And it's like you take whatever model is out there that is working, you just slightly differentiate yourself and you do the exact same thing. You fill up whatever market is there and everything. And don't get me wrong, there's a lot of things to be mad about. Be mad at everything. Not all the time. Or at least I feel that way occasionally, but it's okay. And everybody knows the most adult thing to do when one is angry is to scream into the void that is Twitter. Why? Because people make money saying crazy things. Um, Incentives. Da, 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 da. Okay. Diatribe aside for the moment. All right. What the heck could this mean? All right. Let us assume. Okay, we are within this mass ring. All right, so we fall within this range. Okay. I mean, if it was just this and it got us there, that would be cool. It didn't get us just there. You look, I'm like, all right, it's about a magnitude and some change off. And I look at it, I'm like, well, 8 pi is basically 25. So that'll give me a little over a magnitude or so. And I'm like, all right, it happens to get within there. Now, again, we have 0 significant digits. That is significant, I claim. Like, all right, you want to hit that bullseye. We hit the board. We heard a thud. We hit the board. It wasn't a wall this time. We've hit the board. Okay. We're in the magnitude of the target. We think. And again, this is for the sum. And then you're also going to need to figure out, I'm like, all right, well, if there's different values for different flavors, they have different models. Some models like there's one neutrino, it's massless. Okay. All right. And then there's another one where it's like, all right, no. Maybe 2 are massive, and maybe there's 1 massive. And people have all different models. But then you could also do something where, like our friends, the leptons there, the electron, the muon, the tau, and stuff, they have a very specific mass ratio. Mass of the electron to the muon is about 206 difference, or muon divided by an electron is 206.78, and then the mass of the tau divided by the mass of the electron is like 3,477, yada yada. Don't worry, I didn't memorize this. I just happen to have a little Wolfram Alpha thing open that actually has it here. So it's like, Oh my God, he remember that. Hey, that was one of Dick Feynman's good tricks. Just remember something very specific that's relevant and remember at least a little bit of it, like the VAT number and building number. And he made people at Los Alamos think he was a complete genius. Just, we want to be open and transparent as best we can, right? All right, yeah. So that's where that 3477, because I had already kind of gone through that a little bit looking at the ratios last night. So I haven't even gone through to break up any of these things because that's supposed to be the total sum mass. I mean, that's cool, but now you got to figure it's like, all right, uh, we won't do that right now. I'm sure somebody else can do that if you want. Um, Probably do it after because mostly just going through and just grinding out thing after thing after thing. Yeah, that's gonna take a little while, but I'm like, all right, well, at least 8 pi is it seems to be important within general relativity and everything. We had it in there within our cosmological constant and our other equations and everything. You guys want to say anything or? Oh, okay, all right. Oh, I'm sorry. I'm offering the floor to unwitting participants. That's this is why I don't get invited places. But where were we? Oh, let's go to our other thing on over there. So I'll stop that one. Oh, hey, nerdy. What's going on, my friend? How we doing? What's it get? Yes, you need over 9,000 significant digits. Well, I'm not sure about 9,000, or at least for to differentiate between things and stuff. Now, I would I would be a proponent of saying, as I almost leave the studio on accident, I'd be a proponent of saying maybe we only need 14. Why? Well, all I know is, well, within what is it? Within general no. The Newtonian gravitational constant works for about 7 significant digits, and Einstein gets us about 7 more. And then we go over to our friend over here because we made a couple of videos about this. We can go over those real quick. 7. Oh God, how many 7s do I have? Oh God, far too many 7s. Okay, let's add additional context to our query. Okay. Wow, I say that's all the time. Wow, significant. Mhm. Well, I mean, well, that brings up a good point because if you spend enough time on codata, the measurements and the recommended values only go out to 14 significant digits. That's one of those things where it might get the old noggin a jogging. Here we go. Oh, I'll try a little Professor Penrose. Let's get. What time is that? 7? Okay, cool. Okay, I'll text. Okay, cool. All right, might get to check out a science like fun. Okay, yes. Send me the presentation. The benefits of living in a college town. Yes. Okay, cool. All right. Look, sir. I'll have to do cool stuff and things. So where are we? Oh, derp. At myself here. All right. Professor Roger Penrose on. Excuse me. I was watching some Wolfram stuff. I know. Imagine my shock. Professor Penrose on Newton and Einstein's precision on gravity, and 7 significant digits.
Now, mathematics can also describe things in the ordinary physical world, gravitational attraction, electromagnetic attraction, and with the same kind of descriptive accuracy.
Well, there's another, even more in a certain sense. Newton's theory already had a precision of something like 1 part in 10 to the 7. So that's 10 million.
Wow.
And then Einstein comes along and produces a theory which is now known to have a precision something like 10 to the power 14.
So what does that now begin to tell us about what mathematics really is?
Yes, well, in a sense, this is telling us that our picture of physical reality depends on something in the sense which is more precise, at least in our understanding of it, than how we think about the world. It has its own life in a sense.
Oh, now again, I am not a Nobel Prize winning physicist like Professor Penrose. I'm just appealing to him for an emphasis from an authority figure here. Because is that what people do? We should just be honest about what we're doing, right? But all right, so essentially, the Newtonian gravitational constant stuff, it seems to work. Newtonian gravity works for basically 7 significant digits. Okay, and Einstein comes along and he gives us 7 more. I'm just saying, what if we only actually need 14 significant digits? Now, I am not a mathematician, but I'm pretty sure 14 is less than 9,000. I could be wrong, nerdy. I could be wrong, but typically, I think so. Oh yeah. No. Penrose was very young there because that was from I think like 15 years ago. Yeah, it took because Thad had mentioned that clip. He's like, I think Brian Greene said something about like, oh, Professor Newton gave us like 7 significant digits, and Einstein came and then he finally found it. He's like, oh, it was a Professor Penrose that had said it. So then we found around. It was on Robert Lawrence Kuhn's channel. Shout out to Closer to Truth. Um, yeah. So that was probably maybe even old, about 15, 20 years. So yes, it's Professor Penrose in his 90s now. So I don't think it was in his 90s there. Uh, but see that's an interesting thing. It's like you don't hear that much. It's like people like, all right, we're almost quantized gravity. We're like this will do it here, not this, but whatever the this is at the time. And then some people talk about it, and then you might hear about it 10 years later. And it's hey, maybe that is the way to go. Again, I'm a little biased. Maybe we don't really. Maybe we just need the kind of geometricize the quantum. That's perhaps the big thing. That's because one, we've been doing that anyway, and I know Dr. Weinstein likes to harp on that when he's not going after and saying mean words to people about string theory and loop quantum gravity. It's like uh, don't hate the player, hate the game. That's my opinion there. And again, full disclosure, Dr. Rick Weinstein helped get me interested in this. Why? Because I'm like sure that as no one else in the internet happened to come across Dr. Eric Weinstein on Joe Rogan, where he's talking about spinners and you have to go around twice to actually get it to work and everything. And you're like, whoa, that's rad, man. You're like, how do you even do this? I don't know. How would we go around something like that with like a cup or something? I know that wasn't really good. I need to stretch more, but delicious root beer, slightly watered down by ice. Not my favorite. Again, honesty is important. But nerdy. Nerdy saying, step away from the string theory. Now listen, here's the thing. Also being in a college town, I've gone to like a grad student party or so, and then realized I was not in grad student shape or in my 20s anymore. Was doing the pass out on the couch outside. I managed to get everyone pizza first. Why? Because people like food. And I should have ordered earlier. My stomach would have probably done a lot better. But the whole thing about getting people excited. I remember when I saw that, and he's like, he did it on April Fool's. Dr. Eric Weinstein, he goes on to Professor Keating's and Joe Rogan's podcast. I think he went on to Joe Rogan and it was being released right around the time. And they went live with Professor Keating, and he was going over this stuff, and it was exciting. I'm like, this is cool. I'd like to get involved. I've been spending time with Jen. Shout out to my friend Jen and teacher from the Church of Entropy. Very brilliant woman. Uh, as and then we were like, okay, maybe we should work on this. And then she pointed out, well, if you want to work on this, he's like, send me an email. So I sent him an email, and I never got a reply. And I was like, well, it happened. I didn't hear back, and ultimately, literally within a week of April 1st, 2021, April 6th, 2021 happened. That's when Thad did his source code 7 video where he correctly predicted at least what the value should be according to experimental results of the muon G2 experiment that was released the very next day on April 7th, 2021. So that's kind of like a indirect, a very circuitous route about how I'm here. It's this, I get excited by things. And that's why, like, if people are talking about things and all of a sudden, it's like, I noticed a cool relationship. I mean, I don't see this in the literature. Maybe it's in the literature. No, that's very cool. And it's like, I noticed a cool thing to be like, well, this obviously it explains special relativity, the full Lorentz transform and everything. It's like, I mean, I've heard a lot of words. That might be right, but how about rather than, and again, I'm totally guilty of this still myself. So I mean, a hypocrite, a hippogriff, whatever, one's a mount or a travel method in do people still use griffins to travel in World of Warcraft? I don't even know. It's been ages. I don't know. I hear they have Dragonkin now. Maybe we'll play someday again. Uh, I'm currently filled in addiction with something else. So whatever I do, it's sometimes we go a little bit excessive or hardcore. But let's see, we got. We'll see. Okay, the sad thing is, and this is strictly a. We'll go with a. This is just a straight opinion. There's just a straight opinion here. Again, very biased, couching, yada yada, all that jazz. Okay. If there is something to this, and what I'm saying is that I'm the poster and the model and everything, it might make quantum mechanics boring. It might make a lot of physics kind of boring in a way because it's like, rather than it's like, we have no idea why this is the answer. It's something probability. It's like, well, we got some dimensional stuff and it's doing a geometric thing. Now it might be doing a geometric thing coming in on itself or something like that. And depending on what it is, that might explain a lot because we can geometricize, I don't know, past 7 significant digits. And if you can solve for one piece at a time, I don't know, kind of aren't we just using the standard, was it binomial theorem or something like that? Again, I'm not a mathematician. I'm just like, all right, well, this seems illogical. So even a dude on the internet that somehow ends up as a monk in a physics monastery can actually start to parse that. And that's claim, but then again, you also have a bunch of other stuff. So it's like, all right, so this itself happened to be wrong. It's like, okay, well, let's make it better. It's like, what are we going to become, religious authoritarians about science? I thought that's why a lot of folks went into science, because we don't want certain people that may, and again, I'm not hating on anybody with religion and something. You go your way, I go Yahweh. Listen, if somebody's going to use something to their own personal gain, utilizing perhaps the ultimate authority figure, I don't think that's cool. That's now, if you're doing it to help make things better, and I don't know, I think a lot of folks go into science because it's like, we don't want folks just preaching to it. Because the thing that I learned in sales is everybody loves to buy, nobody likes to be sold. That's the thing. And as soon as you start coming off as a pushy salesman, and I think, and again, editorial, people can get mad and stuff like that. When you start getting into some of those different scientific communities, especially with idea generation and stuff like that, you see it's like, I think occasionally, not always, but occasionally some people talk past each other because why? It's because I have my thing. Can't you see? It's the most important thing. It is my precious. I should probably hold something like a marker. So no, use a fluffy cat toy because, oh, it's my precious. I have my precious right here. It's doing, oh my God. I, I have my precious and it just, it almost just turned off the whole computer. Not quite. I was worried about, oh God, stuff is flying around. All right. Let lion cat toys lie. But I agree. That's the thing. Science and stuff is fun. Now, the thing is, hey, We all have our different. Actually, speaking of cults, let's get a copyright strike, shall we? Or no, here we'll do this. Do I dare open up a social media app? Let's see. No, I won't do that. I won't. Basically, long story short, Sean Carroll was posting on Blue Sky or something. That's the less dumpster fiery Twitter for now. About some of the problems that could happen in science, or some of perhaps the fair criticism, and then I just linked the video cult of personality. It's like da 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 da. It's You can look it up. It's from I believe in Living Color. Uh, but it goes on to how people that can say words in a particular way that may have certain mannerisms. Perhaps they are a very charismatic individual and they can get up and literally just roll complete garbage out of their mouths. And as long as you're saying it with passion and conviction, there will be some people to believe you, because that's what I was trained in corporate sales. It's like, listen, you can literally say hot, not always, but sometimes just the way you're talking to a person, because we're human beings, we're pattern recognition creatures. Again, I'm not a biologist or anything, I'm some rando on the internet. But the thing is, I feel like as human beings, we've adapted over thousands of years to be able to, like, all right, there's another. Seems human. Doesn't seem like it's going to eat me right now in most cases. Okay, okay. You can see it's not making aggressive postures to me. Okay. We've been able to start to communicate and pick up on body language, facial expressions, and different mannerisms and tones. And yes, actually words. Because language is a fascinating thing. And then over the past 100 years or so, it's like we've adapted. It's like, all right, can you hear me now? Yes. Us old fogies from the 90s remember all those Verizon commercials and everything. It's We began to interact and being able to, okay, if you know a person or you spoke to a person on a phone, you can pick up their tones, their language, their cadence and everything as well. So you can kind of get a feel for maybe if they're using an inflection or there's like, ooh, because one of the interesting things is, whom do we curse? Those we love and those we hate. And I'm sure a text-based internet would never complicate anything like that. That ends at 140 to 280 or whatever it is now limit. That's now unlimited, but we only show like the first 280 characters. And we all know that for people that have never met each other, that have no idea what another person is going through at that exact time, obviously communicate perfectly well, and nobody would ever disagree on the internet or IRL. What was I supposed to be talking about again? Something about neutrinos? Yes. Passion and 34 convictions. It's now, surprisingly, I don't think I'm a convicted felon. I probably should be. But those are other things that I'd end a political career in 20 minutes. That is a video that exists in this channel in some way, shape, or form. Good to see you, Rick. But no, we were just conjecturing on neutrinos and stuff, and I just looked at something and I just had a question last night, and I'm like, all right, Professor Keating said something about like a neutrino range, and I look it up, and apparently it's supposed to be between 0.06 electron volts and 0.07 electron volts for the sum of all the flavors of neutrinos. Um, but I just did the same thing that had done for basically the electron. It's like we start off with Planck mass to the fourth divided by what we appear kilograms to the third power, because that gets us one dimension, and then we're putting our unit of kilograms, and then, well, seems like we have about three spatial dimensions. Why? Because eh, eh, ah, yes. And rumor has it gravity is the characteristic of a place. Feel somebody said something like that once. I'm sure somebody can correct me if I'm off, but that's not what we're talking about right now. Maybe it is what we're talking about, and I just don't see the connection yet. Maybe aside from 8 pi, but that's yeah. So no, I just saw that, so I did the same thing. I'm like, all right, well, if it's supposed to be less than an electron, there's 5-dimensional bases of reality. Well, but the fifth power. And if we exist in a 4-dimensional space, let's say kilograms, raise it to the fourth power. Okay, so that gets us about a magnitude and some change off. And I'm like, all right, let's try the fine structure constant. Let's try the square root of it, or Joe one. Oh, did you just do these different things? And I'm like, it's popping around. My some masses go to like 10 to the negative 35 kilograms. It's like this is about 10 to the 38, 39-ish kilograms. I know I probably should have wrote out as that, but these are the simplest numbers to come out. But basically, you take that, it gives you out a mass term, you multiply by c squared to get your energy. And in order to get it to this, if correct, quite narrow range, you multiply by 8 pi. So I'm like, again, my confidence is probably around this number because we still have 0 significant digits. We may have the correct magnitude, or at least according to the literature, we might. But basically, you multiply this by 8 pi, which seems to be a happy time when that happens to be the factor, at least within a number of different things within physics. But yeah, that gives you 0.06885, yada yada, electron volts. All right, so 0.068 is greater than 0.06, and it's less than 0.07 electron volts. Now, again, we have 0 significant digits, but as we increase, well, to be fair, we're going to be running into neutrino fog and stuff anyway. Apparently, there have already been hints of that. What's that? Because as we start to get greater and greater magnitudes of measurement, there apparently is a point where we will be blinded with neutrinos. I remember when I need to find the talk. It was fantastic. Was it the gentleman of the ice cube observatory in the South Pole? I don't know, but they were talking about the hunt for dark matter. And it's like, all right, as they're hunting for axia and WIMPs or whatever might be out there, there is a grave problem in the hunt for dark matter. In that soon, and this was like, I think 2 years ago or so, I believe the gentleman had stated that, yes, within several years, our hunt for dark matter will be obscured by dark matter. Or basically, neutrinos are going to get in the way. Well, neutrinos, as far as we know them, are a form of dark matter. Those and whatever the heck a black hole or whatever is there is. Why? Because, well, we can't see them with our telescopes. Because our telescopes, they seem to be receiving light or some signal that we could be like, that's pretty hot. And all the cold, or I would conjecture crazily that there might be a lot of old, cold, dark matter. Again, my personal opinion is it should be lambda OCDM. Lambda, old, cold, dark matter. Ba-ba-ba. I'm going to hell. Oh, I have been going to hell. But how long has this crazy broadcast been going? Oh, it's been going on for about an hour. Okay, let's see what else. What else do we have? Yes, I know. After the episode with Fizz the other day, God, who knows? Just oh God. Well, I think we've devolved enough for here. So, but yeah, that's all. Just a random little thing, almost certainly wrong. But I just you get some data, you look at the stuff you got, you play around, you see does it line up. It's all right. It's some cosmological conjecture, maybe. So, but other than that, oh hey, look, we're just wrapping up right now for uh, episode 5 of my Monastery Life. So basically, at least Monday through Friday when I have the free time and stuff, gonna continue to try to spend about an hour in the day just going through. Just because all of a sudden it's like, oh, somebody's in the chat. Oh, they make a reference to something. It's like, oh, I didn't even know that was a thing, or I had that completely wrong. Because isn't that this quest of science is to be less wrong or something along those veins? But with that, everybody, have yourself a fantabulous weekend and take care of yourself. It's a crazy world out there, but we're just hoping for the best. I see you interesting and amazing. What's up? We're peacing out. Peace out, everybody.